Hello and thank you for joining my talk. My name is Michael Rehme. I am a PhD student from the University of Stuttgart in Germany. The work I am about to present is joint work with Professor Stephen Roberts from the ANU in Canberra and my supervisor Dirk Pflüger. In this talk, we'll perform uncertainty quantification for a tsunami simulation. Therefore, I want to very briefly give you an idea of the concept of uncertainty quantification. Classical computer experiments use multiple scalar inputs to calculate deterministic scalar outputs. However, the simulation will always neglect aspects of the real world. Uncertainty quantification deals with this by associating with each parameter a probability density function. The density specifies the likelihood of each possible value. In forward UQ, these densities are then propagated through the experiment. Instead of scalar output values, we get stochastic quantities like moments or percentiles. This makes uncertainty quantification capable to treat problems more generally than classical approaches. UQ experiments can become very expensive in terms of runtime and hardware requirements. This is often caused by the curse of dimensionality, which describes the exponential growth of runtimes for increasing dimensionality. Therefore, we use sparse grids, a discretization technique designed to mitigate the curse of dimensionality. Furthermore, we use B-spline basis functions. These have many favorable properties. In this talk, we'll make particular advantage of their differentiability for optimization and their integrability for the calculation of means. In the following, we'll use a single surrogate based on sparse grids and B-splines to perform a thorough uncertainty quantification analysis of a tsunami simulation. The outline of the talk is straightforward. First, I'll introduce the ingredients for our surrogate, sparse grids and B-splines. And then we'll perform uncertainty quantification for the tsunami simulation. The most simple approach for discretization are full uniform isotropic tensor product grids, as can be seen here. The problem is that the number of grid points grows exponential in the number of dimensions, and thus already for moderately high dimensional input spaces, this approach becomes infeasible. In sparse grid context, this full grid is decomposed into several subgrids. For each subgrid, the contribution to the overall approximation quality is evaluated, and it turns out that lower right subgrids are much less important than upper left ones. Consequently, regular sparse grids are defined as the combination of the upper left subgrids. The regular sparse grid of level L consists of the combination of the L upper left diagonals of the scheme. In comparison to the full grid, the number of grid points is drastically reduced, while the convergence rate stays almost the same, given some smoothness assumptions. Note that this holds only for the number of inner grid points. The number of boundary points stays equal to the full grid. Therefore, when increasing the dimension, the boundary points must be omitted, and later on we'll have to modify our basis functions to cope with this. These pictures illustrate just how many grid points and thus function evaluations can be saved by using a sparse grid. On the left-hand side, we see represented as volumes the number of grid points of the subgrids of a full grid in 3 dimensions, while on the right-hand side, we see the same for a sparse grid. Finally, we do not only use regular sparse grids, but in fact spatially adaptive ones. These do not add the whole diagonal of the sparse grid scheme for every level. Instead, only the grid points most important to the quantity of interest are used. This reduces the number of necessary grid points even further. We start with a regular sparse grid of some small level to initially scan the domain. Then we identify the grid point with most influence on the quantity of interest and add all its hierarchical children to the grid. Here, this is indicated in red and blue. In this work, we use the standard surplus criterion to identify the most important grid point. This criterion chooses the grid point which its associated basis function has the largest interpolation coefficient. Because we're using a hierarchical basis, the size of the interpolation coefficients is directly correlated with the local quality of the approximation, and the criterion minimizes the L2 error of the approximation. Now that we have sparse grids, we need basis functions. We are using B-splines because they have local support and as piecewise polynomials can be numerically exactly differentiated and integrated. For the underlying sparse grid, we need to define B-splines in a hierarchical manner. You can see this in one dimension on the right side. We define a knot sequence based on the definition of sparse grids. The B-splines are then defined recursively on this knot sequence as linear combinations of B-splines of lower degree. The B-spline of degree 0 is simply constant. Note that the derivative of a B-spline is again simply a linear combination of B-splines of lower degree. Higher dimensional basis functions are constructed using tensor products. When Schoenberg originally introduced B-splines, he did so on the whole real axis. There, they span the space of splines. However, when restricting ourselves to a finite interval, this property does no longer hold, because the Schoenberg-Whitney conditions are invalidated at the interval's boundaries. This problem can be solved by using the not-a-knot condition. It requires continuity of the nth derivative of all B-splines at the leftmost and rightmost inner points of the domain. This, fortunately, is equivalent to removing these knots from the knot sequence, but keeping them as interpolation nodes. This can be seen in the illustration on the right. The crosses show the not-a-knots, in this case for cubic splines. We use Lagrange polynomials on lower levels, where the not-a-knot condition is not yet applicable. When introducing sparse grids, I mentioned that we must omit the boundary points to further reduce the number of grid points. This again introduces the same approximation problems at the boundary. We go ahead and apply the not-a-knot condition again, removing another 2 knots from the knot sequence. With this trade-off, we can remove 2 boundary knots and their corresponding basis functions without losing approximation quality. Again, we use Lagrange polynomials on lower levels where the not-a-knot condition cannot be applied. We recently showed that this basis spans the space of splines, including the space of polynomials of according degree. Note that in the illustration on the right, there is no level 0 anymore, because this level contained the boundary points we omitted, and thus the sparse grid now starts from level 1. Now we have spatially adaptive sparse grids and B-spline basis functions defined and can go on to the application. The tsunami simulation we're investigating is based on a real event that happened in July 1993. A tsunami hit the Japanese west coast, causing run-ups of more than 3 meters. In a valley on the small island Okushiri, run-ups even reached up to 30 meters. To explain these enormous run-ups, an experimental investigation was carried out. The resulting accurate data was made publicly available. Based on this data, the Hokkaido Nansei-Oki tsunami was simulated in Anuga by Steve Roberts. Anuga is a shallow water equation simulation software developed by Geoscience Australia and the ANU. On the top left, we can see the bathymetry of the domain. The tsunami wave, which can be seen on the lower left, comes in from the left side of the domain. The system is evolved through time, and the run-up is measured in the mentioned valley. The original measurement can be seen on the lower right. Now we are interested in how different shapes of the incoming wave influence the run-up heights. To investigate this, we decompose the original wave into 6 Gauss bumps, which is sufficient to accurately capture its shape. Then, the height of each Gauss bump is made a random variable. We assume them to be IID normally distributed, centered at the original wave. Given a set of these shape parameters theta, we can form a new input wave, which is normalized to the energy of the original wave. The normalization ensures that only the shape of the incoming wave is influencing the run-ups. Otherwise, simply taking larger shape parameters theta would result in unrealistically huge waves and run-ups. Now, we create a sparse grid B-spline surrogate for the tsunami simulation. We do this in our software SG++. SG++ is open source, publicly available, and the most extensive sparse grid library available. The Anuga simulation uses 451 time steps, and accordingly, we create one surrogate for each time step. This sounds expensive, but we use the same underlying spatially adaptive sparse grid for all individual surrogates, and thus have to solve the arising system of linear equations only once. Because evaluations of the simulation are rather expensive, we limit ourselves to 2,500 grid points, which is the number of points of a regular non-boundary sparse grid of level 5. We calculate 3 uncertainty quantification key quantities from our surrogate. The first is very simple, percentiles. They are simply the value below which p% of observations can be found. However, to be meaningful, a large dataset is required, and the runtimes of the original simulation forbid so many evaluations. With our surrogate, however, it is no problem to create a dataset of 100,000 evaluations and then derive the percentiles. The second quantity is the mean. We calculate it using stochastic collocation. Given our surrogate f tilde, we use Gauss-Legendre quadrature to integrate it with respect to the probability density function. Note that the B-spline basis consists of piecewise polynomials, and thus is numerically exact integrable. Accordingly, the quality of the mean is a direct consequence of the quality of the approximation. The last quantity we look at is the wave shape leading to the maximum run-up. For this, we need to optimize the surrogate. The B-spline basis provides access to gradients, so we can use gradient descent to optimize. The step size is determined by the Amijo rule, and we use the maximum value among all grid points as our starting point. For comparison and verification, we use one of the industry standard softwares for UQ, Decoder. This uses polynomial chaos expansion, one of the most popular surrogate techniques in UQ. It is based on polynomial bases which are orthogonal with respect to the distributions. In case of the normal distribution we are using, Hermite polynomials are used. The advantage of polynomial chaos expansion is that stochastic moments can be directly extracted from the coefficients of the expansion and no additional integration is necessary. A downside is that Decoder does not allow optimization based on the polynomial chaos surrogate. So while in SG++, we can use one single surrogate for the calculation of all key quantities, in Decoder, for the optimization we have to again evaluate the objective function. The optimization itself then is performed using the mesh-adaptive direct search algorithm based on the implementation in Nomad. So let's look at the numerical results. In this plot, we can see the L2 error averaged over time with respect to 10,000 samples drawn from the normal distribution of the shape parameters. As mentioned at the beginning, already for this 6-dimensional problem, boundary points are too expensive, and their convergence in blue is worse than the alternatives. These are the non-boundary splines in orange and the Decoder PCE in gray, which perform quite similar. The spatially adaptive grid in solid orange leads to a small improvement and thus a little smaller in error than the Decoder polynomial chaos. The underlying simulation is only first order accurate, so none of the method reaches its optimal convergence rate. All methods stagnate around 10 to the minus 3. This stagnation is likely caused by tiny inaccuracies of the underlying tsunami simulation. But note that the error is given in meters, thus this is an error of only 1 millimeter for a tsunami wave of 30 meters height. Now we look at the stochastic quantities calculated with SG++. They are nicely summarized in this plot, which gives us a good understanding of the possible run-up heights in our scenario. The expected run-up with respect to the normal distribution is shown in orange. Around it are the 5th and the 95th percentile, which illustrate the interval where most run-ups will occur, ranging from 29 to 30 meters maximum height. The optimized maximum run-up is illustrated in red. It is significantly larger than the original run-up and surpasses it by over a meter. Finally, we compare the quality of the approximated stochastic quantities to the coda. SG++ as well as the coda very accurately capture the expected run-up. The average mean error is less than a centimeter for both. Now, when averaging, there might be unpleasant outliers, but even the largest mean error over all time steps is around 2 centimeters for the coda and only around 1.5 centimeters for SG++. The calculated maxima are very close. SG++ finds a parameter combination leading to a slightly larger run-up of 31.06 meters. So, in this talk, I demonstrated how easily an expensive UQ simulation can be examined using SG++. Our approach, based on B-splines and sparse grids, led to a very accurate approximation of the original simulation. Then, exploiting the B-splines, we calculated relevant key quantities and got a better understanding of the simulation. We verified our results using the industry standard UQ software decoder, and for all the quantities of interest, our software SG++ performed comparable or even slightly better than decoder. Next, we plan to not simply use an incoming wave determined by shape parameters, but to couple the tsunami simulation with an earthquake simulation. This will make the simulation more realistic, however, it will also become much more expensive. Furthermore, the number of input parameters will increase, making the problem higher dimensional. With this, I'd like to thank you for your attention, and I'll be happy to answer your questions.